Hey there, folks. How you doing today? Today, we're going to talk about the super duper exciting topic of weathering and erosion and a little bit of deposition when we're done. Weathering, erosion, and deposition, or making, moving, and putting down sediments. Now, through this lecture, we're going to give you some fancy textbook definitions of the words weathering and erosion and, well, probably even deposition. But in the end, I want you to keep it this simple in your brain. Weathering is making, erosion is moving, and deposition is putting down. Okay? So, what are sediments? Sediments, as we typically think of them, are fragments of pre-existing materials. All that riffraff laying around at the surface. Dirt, probably you call it. Gravel. Rocks. Okay? The pieces, parts of much bigger hunks that have broken down over the years into smaller and smaller bits. And those bigger bits have broken off of something even bigger at some point, and it's just an ongoing process. Now, when we think of it in those terms, the word sediment, we want you to know that the material can either be inorganic or organic. Now, we're talking about this in context of, remember our definition of mineral, definition of rock, okay? These can be pretty much anything when we're talking about just the broken up pieces of stuff lying around at the surface, all right? However, there's a second component to the definition of sediment, and that is sediments can also be materials precipitated out of solution. Now remember, precipitate out of solution means something was dissolved in water and it recrystallizes. All right, we talked about that with sedimentary rocks. Now, in this case, we're always looking at inorganic, just like we did with sedimentary rocks, the chemical sedimentary rocks. Even if we were dissolving seashells, by the time you get to the sediment that's recrystallized, that precipitated, it is inorganic. Once it dissolves, it doesn't matter. Now, to go back a step and hopefully not confuse you, if you're looking at those seashells before they dissolve, then that qualifies under this definition. You follow? And then they can be organic. So if you're looking at the crumpled up seashells lying on the beach, that's this. If you're looking at some limestone somewhere nearby that was seashells dissolved and recrystallized, then that's this. Okay? So just to reiterate that last slide there, sediments can be composed of rock material, mineral material, plant, and or animal material. And I think your studies of sedimentary rocks at this point have hopefully shown that to you. And if I'm using this in a future semester, if you haven't looked at sedimentary rocks already, you probably soon will. You see that sedimentary rocks can be made out of all kinds of stuff, from seashells to plant material to rock and mineral grains. Okay, this you need to memorize. I'll be honest. Now, luckily for you, not the diameters, but the order of the sediment sizes. Boulder, cobble, pebble, sand, silt, clay. And luckily it's kind of sing-songy, so you can kind of run it through in your head. Boulder, cobble, pebble, sand, silt, clay. Boulder, cobble, pebble, sand, silt, clay. All right, these are grain size. What do you think? Largest to smallest or smallest to largest? Yeah, largest to smallest, of course. Boulder, and then cobble, and then pebble, sand, silts, and clays. Now, silts and clays, well, any of these have diameters, okay? And if it really mattered, if you were in a laboratory environment, if you were out exploring and you were cataloging the rock types in an area, you would definitely be interested in making sure that your grain sizes were accurate and that you measured them, so on and so forth. In our context, not so horribly important, okay? What I started to say a moment ago, looking at silts and clays, they're incredibly small, okay? Believe it or not, you can tell the difference between the two without even measuring them. And this is where maybe one of the old jokes about geologists eating rocks come from. If you have a mudstone, okay, silts and clays are muds. If you have a mudstone and you aren't sure if it is a siltstone or a clay stone or a mixture of the two, oftentimes what geologists would do is crumble it up a little bit and rub it on one of their front teeth. Now maybe that's from being out in the field for weeks on end and they just want to brush their teeth, or who knows what. But no, in reality, silt would be gritty. You could actually feel a bit of grit when you rub it across your teeth. Clay, on the other hand, would be smooth. Okay, clay would be smooth. Clay would be like flour. Okay, you wouldn't feel much grit with flour. I've never rubbed it on my tooth, but fairly certain that it is that fine. A silt, on the other hand, would still have a tiny bit of grit to it. Sand, coming in at a 1/16 of a millimeter to 2 millimeters. And yeah, I know. Who's mixing fractions and millimeters, right? Those crazy scientists. But at any rate, from 1/16 of a millimeter to 2 millimeters in diameter with sand grains, what this tells us is two things. Sand is both smaller than you would have assumed, and actually larger than you would have assumed. 1/16 is pretty dang small, okay? But 2 millimeters is possibly what some of you might call gravel, just eyeballing it. Not parking lot gravel, but 2 millimeters is right around like Nerds candy, okay? Decent size stuff. But that is, by technical definition, still sand. Pebble is exactly what you would imagine. You've got 64 millimeters, okay, is 6.5 centimeters there. So that's fairly good size. A cobble, you're jumping up to round head of lettuce size, okay? And boulder, well, there is no end. You might not use the word cobble, but boulder, that's a word we use. Gravel is somewhere in between pebble and cobble, speaking about words we already use. And you'll see gravel show up in a handful of folks' tables. It's tables in books and stuff. It's not an official term, but so many people use it that they kind of show you where it brackets there. Again, think, parking lot stones and whatnot. Anyhow, what you need to worry about, again, is boulder, cobble, pebble, sand, silt, clay. All right? And the idea that, these different sediment sizes can make different rocks. Which of these sediment sizes is sandstone made out of, for example? Which of these sediment sizes is shale made out of? How about conglomerate? So on and so forth. All right, so we told you we'd have fancy-dancy definitions. Here is the official definition of weathering. The breakdown of materials at the surface of the earth by the agents of weathering. Breakdown of materials at the surface of the earth by the agents of weathering. And I want to remind you here, I know you're sick of me saying this, but just remember that the surface of the earth can also be underwater, okay? We don't just mean the dry land. Water is not the surface. The floor underneath the water is the surface. Now, erosion. Same idea. The transportation of materials at the surface of the earth by the agents of erosion. I'm going to add the word weathered here. I don't usually have it in here. Today it's bothering me. Just to make that connection. The transportation of weathered materials at the surface of the earth by the agents of erosion. Now at this point you're probably cursing me a little bit, saying, hey, wait a minute, you just told me the agents of weathering and then you switched sides and you didn't say anything. Now you're saying agents of erosion and you're getting ready to switch slides. And don't worry, because here they are. The agents of weathering and erosion are one in the same. That which weathers can also erode. That That which erodes can cause weathering. You've got one more list to memorize here. You had boulder, cobble, pebble, sand, silt, clay a moment ago. Now you need to go with wind, water, ice, and gravity. WWIG. All right? WWIG. Wind, water, ice, and gravity. Remember, weathering is breaking down. Erosion is moving. If I asked you just right now to come up with some examples of how this works, more than likely you're going to come up with mostly erosional things. Remember, erosion is movement. How does the wind erode? The wind blows. Okay? How does the water erode? How does the water move stuff? Well, it flows. Okay? And we will get back to these, and we'll talk about these more in depth. But keep in mind, before we just leave this, okay, from the weathering perspective, the water can wear away at stuff. Water eats away at cliffs. Water rounds stones that are rolling back and forth in the waves or bouncing along in a stream. The wind, sure, if it blows really, really strong, it could break something, but the wind typically needs a tool. An agent needs a gun, if you would. The wind picks up small sediments and throws them around, blows them around like sandpaper. Okay, a lot of those fancy formations out west. I always cite Wile E. Coyote, Roadrunner Coyote show. Okay, all those crazy designs out there. Many of those, some were also carved by water, but many of those, just thousands and thousands of years of wind blowing sand and slowly wearing away at the rocks. Amazing stuff. Ice and gravity, a little more complicated. As far as transportation, they're thinking about ice in the context of glaciers. Okay, glaciers transport a lot of material. It gets sucked up in them, kind of like a big blob, and when they melt out, they move that material. Ice itself is a very powerful force. As far as weathering goes, it can break rock. Okay, whether you're looking at a small scale, a crack in the road, that freezing thawing over and over again, it breaks that crack open. That's where we get our potholes from. To a glacier itself, the giant hunk of ice carving out a valley even bigger than it was. It's an immense force. So that's ice. Gravity, well, gravity falls, right? Things move downslope due to gravity. That's the erosional aspect. Whether you're on a hill, a cliff, or in a stream, okay? Things move downslope due to gravity. Gravity as a weatherer, well, again, we talked about wind needing a tool. Just falling isn't going to break something, but when it lands, okay, it usually breaks. All right, so a little more in-depth time now. Weathering, the production of sediments. The production of sediments. Remember, weathering makes sediments. I want to talk about two types of weathering. Physical weathering and chemical weathering. Now, some folks, some books here and there still use the word mechanical. I've not heard a human being use the word mechanical weathering in a long time. And even in books, for as long as I can remember, they pretty much just put mechanical in parentheses and say, some people say this. So I think at some point we'll just probably stop using the word mechanical. So physical weathering and chemical weathering. Let's talk about physical weathering first. Physical weathering is, guess what? The physical breakdown of rock. It breaks rock into smaller pieces. All right. You take one rock in your hand, you bash it against another rock, and one of them's going to break. It's physical weathering. Wile E. Coyote gets at the top of his hill with that giant boulder, wants to squish himself a roadrunner, and he pushes that boulder down the hill, and by the time it bangs and bounces and bashes against all the other rocks on the way down, by the time it gets down to in front of the roadrunner, it's a tiny little pebble. Remember that episode? It's out there at any rate. So that is what you probably considered physical weathering to be. There's a term for it. I think you'll see it soon, but just in case, the word is abrasion. Abrasion, A-B-R-A-S-I-O-N. Abrasion is rock against rock breakdown. Abrasion. There it is. Abrasion causes rounding. All right, we just kind of talked about rounding a moment ago. You guys are used to me talking ahead of my slides. So I mentioned the rounded rocks you might find at the beach where there's waves, or in a stream bed where rocks have been rolling around for a long time. Mother Nature was the first rock tumbler, okay? We simulate that with these cool, noisy, smelly machines that we tumble and polish and smooth out rocks with at home or in the lab. You go to a museum and you buy all these pretty polished stones. Mother Nature's been doing that all by herself forever. The process is called rounding, all right? And it's called rounding because it takes rolling back and forth, banging against all the other rocks, tumbling through the water. It takes the rough, sharp edges off first. And if you stop and think about that, it makes perfect sense. The reason it's rough, the reason it's sharp is potentially because it's so thin, right? So it's one of the more delicate edges. It's going to be one of the first parts to break off. So we look at rounding as an indicator of how long something's been in the environment, whether it's fresh sediment or whether it's been eroded a lot. Okay, and there are folks out there, believe it or not, that care about such stuff, sedimentologists and whatnot, which, yes, you can get a degree in that. So abrasion is rock against rock breakdown. Abrasion causes rounding. Rounding, a great example, or a great way to think about that, is the rocks rolling and tumbling back and forth in the waves or a stream. Next, we want to talk about a different kind of physical weathering called frost wedging. I actually mentioned this one too when I talked about the water getting into cracks in the street and freezing and thawing and freezing and thawing and eventually making potholes. All right. Well, that happens in regular rock material too, not just in our blacktop. Water expands when it gets cold. That's kind of the opposite of most everything else on the planet. Most things most things expand when they get warmer, contract when they get cooler. As it turns out, though, the crystalline form of water takes up more space than the liquid form. You have ice cube trays, and you're in charge of filling them up, and you go the next day and pull some out, and you see these ice cubes that are up almost right to the rim, or even sometimes higher than the rim, and you're like, how in heaven's name did I fill up this tray so much that I actually, was above? You didn't fill it up that high, okay? When it froze, it expanded. One of the other ways people unfortunately learn about this is if you leave a bottle or a can out in your car during the winter time, or you stick one in the freezer to cool off rapidly and you forget about it. Sometimes they explode, right? All right. There's a little more going on in the sealed can environment there, but again, the idea is that the solid form of water takes up more room than the liquid form. So out in nature, what happens when you get into late fall, early spring, when you bounce back and forth between warm and cold, water gets down into all the cracks and crevices. Sometimes it freezes, and believe it or not, it's strong enough to wedge that rock apart just a little bit, make that crack just a little bigger. And then the next time it happens, that much more water can get in. And when that freezes, it wedges it apart that much more. It takes a long time, okay, for this to happen, but it is a thing. And there's more examples in your book. I just picked 2. All right, I'm going to stop this video here, and we'll pick up the next video with chemical weathering.